Hello, this is Russell Klein of Siemens EDA. I'm going to be talking to you today about the verification of inferencing algorithm accelerators. The content of today's talk was partially developed by Petri Salanti, one of my colleagues. He's not able to be here at the presentation today, so I will be covering all of the slides, but I did want to credit him with the creation of the content. This is the agenda we'll be going over today. We're going to start by talking about AI accelerators, the different kinds of accelerators, how they can be used, to clarify exactly what will be, which accelerators we'll be talking about in the context of verification today. Then we're going to talk a little bit about high-level synthesis. High-level synthesis is an integral part of the verification and design flow that we're going to be talking about, so we want to give you a little bit of background on that. Then we're going to talk about optimization of inferencing accelerators, what that type of optimization looks like, and how that affects the verification that you're going to be doing. Then we'll be going into specifically how you'll go about verification of that inferencing accelerator, all the way from the Python down to the RTL. And finally, we'll be tying it all together with an example algorithm. Specifically, we'll be using a weight cord inferencing algorithm, and we'll show how this gets pulled through the verification flow and what our results were. So we'll start by talking about AI accelerators. We're going to be talking about deploying these inferencing systems and describing where and how that inferencing can take place. One option we've got is to use a cloud-based machine. We could take a server that was in the out on the internet somewhere, such as an AWS machine or an Azure machine. We could send up our measurements and perform the inference on that cloud machine and get the results back over the internet. If we had more stringent response time requirements, we might want to take advantage of a machine that happened to be on our local area network. Some gateways have been augmented with inferencing hardware, which can be used to perform those inferences, and we'll get a more reliable response time. But there's a certain set of inferencing where the response time or security or privacy requirements mandate that we perform that inferencing on the edge device itself. Now, as we go from right to left, what we're going to find is that we get higher latency, but we also get lower development costs. If we simply take advantage of a cloud machine, we can load it up with some open source software and be up and running in almost no time. A gateway machine might need a little bit of porting, but would be very little. However, on the edge, we may have to do some custom development, and we may even want to do custom development to get the highest performance or the greatest efficiency. Now, how are we going to go about performing those inferences? We could do it on a standard CPU. Another alternative is to use a GPU. A GPU would be higher performance, but it also generally has higher power consumption. There are dedicated NPUs, neural processing units, or TPUs, tensor processing units, and these devices are generally going to be faster and more efficient than a GPU because they offload some of the graphics capability that you typically see on a GPU. So they're more focused to the task of inferencing. If we've got an edge-based system, we might specifically use an edge-based TPU. This won't be as fast as a server TPU, but it'll be far more efficient. And finally, we could build an FPGA or an ASIC implementation of our inferencing, and this would give us the highest performance and efficiency. So as we go from left to right, what we're going to find is higher levels of specialization, but the inferencing will be performed using less energy. So the CPU would be the most energy hungry, the ASIC implementation, the lowest. What we're going to be talking about in today's discussion is those systems where we're performing the inferencing on the edge, and we really need the highest level of performance and efficiency. So we're going to be talking about developing specialized inferencing hardware, which would be intended to be used directly on an edge device. So if we look at kind of the universe of different deployment opportunities, our slowest and highest energy would be the CPU. We get better performance and efficiency on a GPU, and yet even better on the TPU or NPU. But if we really wanted to get the highest performance and the most efficiency, we would need to do a complete custom implementation, which would give us both better performance and lower energy than any of the off-the-shelf implementations. So if we look at the accelerated AI SoC ecosystem, we've got some AI IP developers, and these could be targeted at either an off-the-shelf solution or a custom solution. When it goes into an off-the-shelf solution, that IP would go into a general purpose chip, and this is an embedded microcontroller of some sort that would generally contain processors, a variety of peripherals, but would really be targeted at a broad set of general purpose problems. That would then be incorporated by board and system level developers in a disaggregated marketplace. So these would be very generic implementations of the AI acceleration IP. So they would be things like arrays of multiply accumulate, systolic arrays, or TPUs or NPUs. If we look at the IP that's targeted at a custom solution, we would be building an SoC not for the general market, but for a very specific implementation for internal customers that would be building a system that would take advantage of that SoC. This would be a vertically integrated flow, and this is the type of AI accelerator that we're talking about. One that's not built for a broad selection of inferencing, but one that's been highly customized and tailored to a very specific problem, and then the efficiency maximized for that. So if we think about the verification challenges around delivering this, if we deploy our inferencing on a CPU, a GPU, or a TPU, we're going to need to verify that our algorithm runs on that IP. We're also going to need to verify that the IP is correctly integrated with the rest of our SoC and the rest of our system. But the IP itself is going to assume to be correct from the IP provider. We're certainly going to do enough verification to make sure that indeed it is working, but it won't be a rigorous and exhaustive verification of that IP. Again, it's assumed to be good from the IP supplier. Now, if we're making our own bespoke accelerator that's going to be used within the SoC, we're going to have to, of course, we still need to verify that the algorithm runs on the accelerator. We want to verify that the accelerator is correctly integrated with the rest of the system. But we also are going to need to verify that the accelerator functions correctly. Since it's something that we're developing, it's our responsibility to verify that as well. So if we look at the design flow from algorithm all the way out to hardware for a machine learning accelerator, again, this is something that is bespoke and is targeted and very heavily tailored toward one specific problem. We're going to start in one of the machine learning frameworks, either TensorFlow, Caffe. There's quite a number of them. And these would typically be in a Python environment. Here, data scientists would iterate to find the optimal neural network architecture. Once they had found that, they would export it into a neural network, and ultimately that would then be handed over to the hardware team, which would implement the system, that neural network, as a set of Verilog logic and state machines, which would deploy the neural networking algorithm. Now, the challenge that we've got here is that we need to make sure that this implementation works the same as the original Python. And in order to check the accuracy and the correctness of that neural network deployed in Verilog, we're literally going to need to run thousands, maybe tens of thousands of inferences. Now, down at the Verilog level, this is going to be very challenging for us. For YOLO Tiny, which is an object recognition algorithm that I've spent some time working with, an RTL simulation for a single inference down at the RTL level typically takes about 28 hours. Now, if we're going to run thousands of inferences, this represents a very significant amount of computation time. Now, we might want to try and push this into hardware acceleration, either an FPGA prototype or an emulation system. But the reality is, at this point, we're still very early in the design cycle, and hardware acceleration is usually not available and is difficult to get in place this early in the design. So we're going to propose a potentially better path. Of course, we still start in the same machine learning framework in Python, and we would then iterate to find the optimal neural network architecture. That would be deployed in Python. But the next step would be to convert it into a C++ implementation of that exact same neural network architecture. We can then prove equivalency between the Python and the C++. The next step is to do an automated conversion using high-level synthesis from the C++ into Verilog. By doing this, we can verify that the C++ is correct, and then when we need to prove that the Verilog is correct, we can take advantage of equivalency checking between the C++ and the Verilog, which will dramatically reduce our verification requirements. So in a little bit more detail, we're going to take that Python neural network architecture, convert it into a C++ algorithm. We will then go through a quantization step, and this is going to reduce the size and potentially increase the performance of that neural network. Next, we're going to go into an architected implementation. And architecting the implementation means realizing parallelism and setting up the data paths within the C++ that we're going to feed into the high-level synthesis tool. And this allows us to have an efficient implementation. And then we're going to run it through the high-level synthesis compiler to realize the RTL. Now, when we've quantized the algorithm, what we may find is that we might want to either add or remove layers or channels within a layer in order to fully optimize that quantized algorithm. And as we're architecting the solution, as we're bringing in parallelism, we may find opportunities where we want to make modifications to the base neural network architecture as well. So there may be an iterative loop going from these two stages back into our machine learning frameworks. And ultimately, we will do an equivalency between the synthesizable RTL and the C++ architected implementation. Now, once the synthesizable RTL has been created, we can pass that to the traditional backend tool flows, and it will work just like a hand-created RTL. So now what I'd like to do is talk about high-level synthesis, as this is an integral part of our design and verification flow. What is high-level synthesis? High-level synthesis is an automated path from a C or C++ or potentially System C description of that algorithm into a technology-optimized synthesizable RTL, which embodies that same function. So essentially, we're going to be taking in a program, an algorithm described in one of those languages. The high-level synthesis system will parse that source code. It will determine an equivalent set of state machines and logic in the synthesizable RTL targeted at the specific technology, ASIC or FPGA, that we're going to implement this in, and generate a set of synthesizable RTL that embodies that exact same function. High-level synthesis features include the user's control over the architectural implementation. So if we think about parallelism, throughput, area, and latency, these can be controlled by the user through loop unrolling and pipelining directives within the tool. Memory data elements can be stored in memory or in registers. This is a resource allocation phase. But the user has the ability to direct the tool to either take the data and hold it in registers, which would be fast and highly parallel, or memories, which would be more efficient but serial. The user does exploration of different implementations by applying constraints within the tool and not by directly changing the source code. So by affecting a number of different switches on the compilation technology, they can explore a variety of different goals within the synthesis process without touching the original algorithm. We can use bit-accurate data types to be able to equivalently model the numeric operations and the numeric storage within the design at both the C++ level so that it matches the RTL level. And the synthesis process can be aware of the goals and is aware of the underlying target technology, either FPGA or ASIC. So the system can be tuned to either optimize for area, latency, or some combination of the two. And being aware of the target technology, either FPGA or ASIC, makes it easy to migrate from FPGA to ASIC or between different ASIC libraries. The benefits of high-level synthesis is that we've got faster design. Typically, an RTL design phase can be done about twice as fast for novice users and up to about 10 times as fast for experienced users. Now, beyond just the RTL design phase, there's verification and a variety of other steps. So if we look at project start to tape out, we've had our leading customers report that that phase can be up to 4 times faster. We also have faster verification. The algorithm can be verified at the abstract level, and then formal and dynamic verification can be used to prove equivalence between the C++ and the HDL. So we don't need to run nearly as many cycles down at the HDL level. And finally, we've got easy technology targeting, retargeting, and retiming. So the RTL can be mapped to a new technology library, a new clock frequency, simply by resynthesizing. And this makes it easy to migrate from an FPGA to an ASIC. So how does high-level synthesis work? High-level synthesis will parse the original algorithm and create a controlled data flow graph from that initial implementation. And this embodies the entire algorithm that was described in that input C++ or System C source file. It then constructs a set of state machines and control logic to be able to implement that controlled data flow graph. It then maps those into resources or the various registers and multipliers and adders throughout the design. It will then schedule those state machines and observe where sharing can take place between the different state machines to minimize the area. And it will do a timing analysis to ensure that the resulting RTL can close timing in RTL synthesis very easily, because it has a complete understanding of the target ASIC or FPGA library. It knows what primitives can be used, how many combinatorial elements can be stacked between registers, and so forth. So it will very carefully construct that to be able to be targeted to the RTL. Now, the verification in the RTL flow looks a bit like this. We start off with our system C++ design, and before we even pass it into the high-level synthesis, we can do a set of design checks. This is static analysis where we can look for coding bugs, we can look for, we can look for the correct synthesis style, and we can find out-of-bounds references for arrays and things of that nature. Once we go into HLS verification, we can bring in synthesis-aware coverage, which will allow us to ensure that our test cases at the high level are fully exercising the design, even after it will be fully unrolled through the high-level synthesis process. We've got abstract test benches, which can be used to run against that. Once we've generated the RTL, this can then be passed into a UVM test bench where we can take those same stimulus, run it against the test bench, and prove that we've got equivalency between the abstract representation and the RTL. It also includes a formal verification between the abstract implementation and the RTL. Now we're going to switch gears a little bit and talk about accelerator optimization. So if we look at the accelerator that we're going to take from our machine learning framework, there's a number of things that we want to take advantage of as we move it into a bespoke hardware implementation. The first one is looking at the neural network architecture itself. Neural networks that were created in a machine learning framework are very typically done in such a way as to maximize the accuracy. As we look to performance and efficiency, it may make sense to modify the neural network architecture, changing the layers and channels within the layers for a more optimal implementation. We'll also want to do quantization, and this involves changing the representation of the numbers that are used throughout the neural network. So the numeric representation of the weights and features can be reduced from what's typically used in the data centers. And finally, we'll look at data moving and storage, alter the way that the data is moved and cached, and look at the access patterns to minimize the cost of the movement of the data. And data movement tends to be one of our limiting factors in terms of overall performance. So this can have a very significant effect. So to review, our high-level synthesis AI design flow starts in the machine learning framework. We're going to be going from C++ algorithmic down to a quantized algorithm. When we quantize, we may go back to our machine learning framework. We're then going to architect the algorithm. This is where we bring in parallelism, we unroll loops. We take advantage of the data movement. And again, when we do this, we might find opportunities to further optimize our network going back into the machine learning framework, and then ultimately running it through high-level synthesis. So, as I mentioned earlier, most neural networks are architected for accuracy on servers. Reducing the number of layers and the number of channels in each layer is going to impact the accuracy. Now, if you ask most data scientists, how much accuracy would you give up for being able to make the neural network smaller or more efficient, usually they'll say none at all. But if you point out that by reducing the number of layers and channels, you would have a small impact on accuracy, say less than 1%, and a large impact on performance and efficiency, say greater than 90%, most data scientists would then say, well, okay, if I can get that big an impact on performance and efficiency, I'm willing to take a small hit on accuracy. Here is a graph of some work that we had done. This was specifically looking at the MNIST handwritten character recognition from one of the LANET implementations done by Jan LeCun very early on. This is a dense layer that started off in Jan LeCun's implementation, which had 500 channels. And so what we did was a sensitivity analysis to look at, do we need all 500 channels? What if we went to 499 channels? Would that impact the accuracy? Because it certainly does reduce the number of computations that we need to make. And what we found is that indeed going from 500 down to 100 sees very little reduction in accuracy at all. And in fact, we can go down to 50, even down to about 25 with a very small reduction in accuracy. Now, a little bit beyond that, and of course, the accuracy falls off rather dramatically as we get towards zero. But we can take away roughly 90% of these channels and not have a meaningful impact on the overall accuracy. So here's an exercise we did. Again, this was on the MNIST handwritten character recognition, where we could quickly go through a lot of different scenarios. So as originally written, the original MNIST network had 12 million MAC operations and almost 5 million parameters. Now, these numbers are tiny on the desktop, but if we have a constrained embedded system, we might like to do something a bit more efficiency. The overall accuracy of this network as defined was 98.75%. When we optimized this network, looking at the sensitivity for reducing the number of channels and number of layers, we were able to get it down to 500,000 MAC operations, 145,000 parameters, with an accuracy of 98.46%. So about 0.3% in terms of accuracy, with a 90+% reduction in the size of that model and its computational complexity. Now let's look at quantization, the size of the data that we're going to store and the size of the operators that we're going to implement. If we can use a fixed point multiplier rather than a floating point multiplier, we're going to save about half the area and about half the energy. Multipliers are proportional to the square of the size of their inputs. So if we're going to go from a 64-bit multiplier down to an 8-bit multiplier, we get a dramatic savings in area. And so anything that we can do to shrink the size of the data operators is going to have a huge effect on our multipliers, and it's going to have a linear effect on our data storage and data movement. So for example, if we go from a 64-bit value to a 16-bit value, we need 1/4 of the storage. And in a given bus cycle on a 64-bit bus, instead of moving one data value, we'd be moving 4 data values, which effectively means we can probably run the entire network 4 times faster. So what we find is that rather than using a 64-bit floating point or a 32-bit floating point, moving to a fixed point implementation in a bespoke accelerator means that we can have any number of integral bits and any number of fractional bits. So the fractional bits can be removed from the low end based upon how accurate, how much precision we need in those numbers. And again, this is where we would do a sensitivity analysis of gradually reducing the precision until we saw it significantly impact the accuracy of the network. On the integer side, typically the data in neural networks is normalized to between -1 and +1. So usually the high order bits within the numeric representation are constant zeros. Simply removing those constant zeros from the design just makes it smaller and more efficient. So this gives us the ability to dramatically reduce the number of bits that we're using. So essentially, we want to convert the weights and features from floating point to fixed point, and then eliminate the high order bits. Again, this is going to remove constant zeros from the design, and then reduce the fractional precision. And of course, we do this as an iterative process to be able to look at the sensitivity of how many fractional bits do we need to have within the design. So as we look at our wake word algorithm, what we found is that the percent accuracy that we needed could be taken down to about 13 bits. And this is in our dense layer. So we had a constant accuracy down to 13 bits and then a significant reduction in accuracy. So we don't need 32-bit multipliers. We could get away with 13-bit multipliers. And those are dramatically smaller. This is another exercise that we had done on MNIST, where we did a sweep of the fractional bits and a sweep of the integer bits. And so this is the accuracy versus the bit size. And so here we have 98.05. That exactly matches the 32-bit floating point. So if we're down at 16 bits, these multipliers are going to be about 1/4 the area of the equivalent floating point, and we get exactly the same accuracy. But we can go further. We can see that the optimal point is probably 6 integer bits and 4 fractional bits, which gives us 97.76% accuracy versus the 98.05 with floating point implementation. But the area and power for those 10-bit multipliers is about 20 times smaller than the 32-bit floating point. So using 5% of the hardware, we can get almost the same accuracy. The next thing that we want to do is look at saturating math. So when we're using floating point representations, an overflow is almost impossible to happen. Using 64-bit floating point representations, we can hold numbers up to 10 to the 308th power. Using a reduced precision, as we take away integer bits and fractional bits and represent the numbers in a fixed point representation, it is much more likely that we're going to encounter overflows because we're going to size this right at the edge of where it impacts the accuracy of the network. Now, an overflow would, that included truncation, would corrupt the result of a particular operation, and all the downstream operations from that would equally be corrupted. So saturating math can be performed where, rather than overflowing and truncating, what we do is, if a particular operation exceeds the storage capacity of representation, we simply use the biggest value that could be stored, or if we're down on the negative side, the smallest number that could be stored. For many neural networks, it turns out that when the number gets large, the absolute magnitude is not important. It's just the number. We just need to know that the number became large. And so this type of operation, although it tends to be imprecise, lends itself very well to a bespoke implementation of an accelerator. So what we find with saturating math, here we did a sensitivity analysis of fixed point numbers with overflow and fixed point numbers with saturating math. And what we find is that typically we can get 1 or 2 more bits. Here we have with 1 additional bit, we do not lose any accuracy. And with 2, we're going to drop down some amount of accuracy, but it's not all that significant. So for many algorithms, we can, and using the saturated math would allow us to use roughly 1 to 2 bits fewer than without it. Next, I'm going to talk about data movement and storage. The movement and storage of the weights and features is going to have a very major impact on our performance and our power. Reducing the numeric representation, as we've talked about in the quantization, is going to have a linear effect on our storage costs and our movement costs. So again, if we could shrink down the size from 64 bits down to 16 bits, what we're going to find is that we'll be able to move that data 4 times faster. Now, we want to ultimately target bus sizes and values that are transferred on the bus to sizes of powers of 2, because this allows us to fully pack the bus with data. So what we may find is that our optimal implementation is 17 bits. Now, we'd really like to get down to 16 bits because that allows us to more fully utilize the buses and memories within the design. So one of the things we find is that reducing the size from 17 to 16 without changing the neural network architecture we may not get the accuracy that we're using. But by changing the architecture, we can offset that change. So it's entirely possible that we can go in and increase, add a layer into the neural network, or potentially even just add a few channels and go from the 17 bits down to the 16 bits. So this is a process where we're going to need to attempt to balance this out. And it'll become an iterative process where we may want to go back to our machine learning framework, change that neural network architecture so that we can hit these powers of 2, which are going to optimize our use of this resource. Another thing that's important is the order of operations. So specifically in the convolutions. The convolution algorithms are going to access the input feature map and the output arrays multiple times. How many times is going to depend on the exact nature of the convolution function. Early in the network, there's a tendency for the input data sets to be smaller than the output data sets, and it means that they're going to be referenced less frequently. Later layers, we're typically going to have larger input arrays and smaller output arrays. And what we want to do is figure out in the design, is it optimal to cache all of the inputs so that we fetch those once and then make repeated references to the outputs, or vice versa? And it turns out that depending on the size of the network, the amount of area that we've got at our disposal, and a variety of other conditions, we may want to change this. We may even want to change it at different points in the convolution algorithm itself. And this is a type of optimization that simply can't be done in general purpose hardware, but it does have a very big impact on both the performance and the power consumption of the design. So what we want to do is cache and buffer those values so that we're minimizing accesses outside of the accelerator, and even more importantly, accesses off chip. One of the things I did here was looked at the post-place and route implementation of one of the inferencing accelerators that we've created. What's notable about this image is that you see lots of blocks. Those blocks are actually memories, and if the combinatorial logic is actually dwarfed by these. So we find that typically 90% of the area of the accelerator, sometimes more, is consumed in memories and not in the multipliers and combinatorial logic. So very effective reuse of the data and caching it effectively is going to have a very big impact on accelerator optimizations. As we go through the example coming up toward the end of the talk, you'll be able to see this more clearly. So accelerator optimization. So as we look at the CNN as it's defined in the original Python versus how it's implemented in Verilog, we're going to find that it goes through a number of very significant modifications. And because of this, it means that we can't do just a straight up comparison between the original Python and the Verilog. And that introduces some verification challenges. And we'll talk about those verification challenges next. So just to quickly review, the verification of our inferencing systems, we need to verify indeed that the individual operators, the multipliers, the adders, all of the different primitives are working correctly. We want to make sure that the processing elements that are built out of those are working correctly and are connected correctly. So the multiply, accumulate unit, and other processing elements that we might make out of those primitives. And finally, we need to verify that complete inferences are working correctly. One of the challenges we have here is that neural networks are robust to failed individual operations. A single correct inference through the hardware or the Verilog implementation does not tell us that we've got a correct implementation of that inferencing algorithm. We can have we need a statistically significant number of inferences to be able to indeed conclude that we have a correct implementation. In fact, it's a bit more involved than that. So if we had a single multiply go wrong, we could run an inference, and at the end of it, we might get a correct answer. We certainly, for example, in an MNIST environment, we could, with several failing multiplies, we could still identify that a handwritten 3 was indeed a 3. Now, bear in mind that the performance within logic simulation is prohibitively slow. I mentioned that 28 hours for one inference in an object recognition algorithm, running the entire design at the RTL level on traditional logic simulation on a desktop or a server machine, it's prohibitively slow. And again, hardware acceleration is rarely available at this point. So verifying at the abstract level and proving equivalence is the approach that we want to take. And this can be done between the Python and the C++, and then between the C++ and the RTL. Now, in our traditional UVM flow, we would have a predictor, and the predictor would ideally come from the originating algorithm. And we simply can't make that work here, again, because we've made so many changes to our machine learning accelerator. We've changed the numeric representation. We've potentially changed the number of layers, although we could implement that in our predictor. But changing the numeric representation and changing the way that we handle rounding and overflowing and things of that nature simply make the predictor from Python unacceptable in this traditional UVM flow. Again, that was because of all of the changes that we've implemented in the Verilog CNN. We no longer can compare the outputs directly. And one of the problems is that if there is a problem, the debug becomes very challenging. So if we look at the verification landscape, we of course have the original machine learning framework that typically running on a desktop machine and taking advantage of the GPU, which is almost always present on one of those, we could typically run some number, tens of thousands to hundreds of thousands of inferences per hour. If we then need to jump down to logic simulation, we're going to get, the scale isn't quite correct. It'd probably be 0.0001 inferences per hour, maybe 0.01. If we brought emulation into the mix or FPGA prototyping, we might be able to run hundreds of inferences per hour, but these are often available very late in the design cycle. So if we have an algorithmic C++ model, we're going to be able to run thousands of inferences per hour. With a quantized C++ model, a bit slower than that. And our architected model, which included the data flow and the parallelism, that would give us something probably in the hundreds of inferences per hour. But here, we can still take advantage of desktop hardware and verify indeed that the implementation is at a statistical level. We can show that the inferences are working correctly. So we want to do absolutely as much verification as possible in the most abstract of these different models that we've got, and then verify equivalency between the different models at each step. And this is really the key to making the verification of the accelerator viable, right? And so it is proving that the Python matches the algorithm, matches the quantized algorithm, matches the architected algorithm, matches our synthesizable RTL. So the first step is to look at Python to C++ consistency. And the way that we would do this is take our original Python neural network, and we would take a single node, and the single node would be available in C++, and we would give it the same inputs that the equivalent Python node had, and then we would run a comparator. So both the C++ and the Python are going to be running in parallel. They both have the common data types between them. If we're using 32-bit floats in one, we should use 32-bit floats in the other. So the only differences in the math here should be in the order of computation rounding errors. So it's entirely possible that if we do our multiplies and adds in a different order, we're going to get very small differences in the lowest significant bits in our mantissa, and that is to be expected, and that's just from the differences of order of computation. Now, importing our C++ function into the Python universe can be done a number of ways. I typically use C types, but there's a host of ways of doing it, including CFFI, PyBond 11, and Cython. Now, once you've proven that a single node works, you go on and prove the next node works, and the next node, and then finally an entire layer. Go to the next layer and do a few nodes in there and slowly expand. And you're just going to repeat this process until we have an entire C++ CNN and an entire Python CNN. And we've proven at a node by node level, inputs to that node, outputs to that node, and we've compared all of them. We can now say our C++ matches our Python. And we want to do coverage in this flow as well. Now, the next thing we're going to do is take this C++ model and we're going to quantize it. So we've now got two different C++ CNN model representations. We've got our network from the original float32, and we've got our network, which is now using a algorithmically correct data type. And so this is the bit level representation within a C++ class that we can plug into this network, and so we can do bit accurate data types. So the only thing that we've changed between this neural network and our quantized neural network is the type of the data that we're operating on. All of the rest of the code will remain exactly the same. And now you're probably thinking, well, that's easy, nothing could break. And you'll find out that indeed lots of things can break. Fundamentally not in the operation itself, but we're going to be storing data in various memories. They're going to be in cache memories, they're going to be in external memories, the weight memories, and so forth. Now, as we move it from a 32-bit value to, say, a 9-bit value, we're going to be we want to pack those values into the external memory, which means all of our offsets will have moved, and the boundary between arrays may or may not happen on clean breaks within the address space of the particular memories. And so you are going to need to bring in some logic to be able to handle all of that, and it's a rich place for bugs to creep in. And so even though the core algorithm is going to change, the data movement and the data representation and its storage will be things that need to be rigorously verified. And so the quantized implementation is now going to be compared, and we again do it node by node, layer by layer throughout the entire design. But here we're looking at the floating point operation versus a reduced bit width fixed point operation, our algorithmic C data types. And the differences will exist, and the differences may be large, and we need to look at all of those and ensure that we've got a correct implementation of them. So the errors that are going to creep in at this level, or they're not necessarily errors, they are differences between the floating point values and the quantized values. The first one's going to be a quantization error, and this is the change in value from the original floating point number to the quantized number as we move it from one representation to another. We will have saturation errors, and that's where we've added up a set of numbers that exceed what can be represented in that fixed point number, and then it will just go to the saturation state. There we can get even bigger errors. And then accumulated errors. As more and more operations are performed, we've got a little bit of drift in each one of these operations. If we've got hundreds of operations, that drift can accumulate. We're going to be significantly off between the fixed point number and the floating point number, but the operation, the implementation was correct. One of the things that can be done here, typically we will truncate numbers, adding a little bit of hardware, we can do rounding, and that's going to help with the accumulated errors to minimize those. So if we look at what level of error or what level of differences are we going to see between the fixed point and the floating point, the C++ to our quantized model consistency, let's say that we had a 5-bit representation for our fixed point numbers, and we're going to compare it with the floating point numbers. So the range that we can represent here is from all ones to a 0 and all ones. And so that's going to represent our smallest and our biggest number. Our smallest number will be -4, and our biggest number would be 3.75. Our fractional precision is 0.25. So each 0, 1 represents 1/4. So floating point math, we could have 1.377 added 4 times together. And in floating point, we're going to get a 5.508. Now, if we take this 1.137, we put it into our fixed point representation, the difference, that's going to be stored as 1.5. 1.5 is the closest value to 1.377 that we can represent in this 5-bit fixed point number. And so when we add 4 of those together, we're going to end up with 6 and not 5.508. So the error being 0.492. The maximum possible error that you're going to see is 1/2 the fractional precision times the number of operations that we're performing on this. And so again, if we've got a large number of operations, a little bit of error each step of the way can potentially get us to a large difference. So if we were not using saturated math, when we added these 4 values up, we would overflow and end up with a value of -2. That's clearly incorrect. Using saturating math, we're going to get an answer of 3.75. Again, it's not 5.508. It's significantly off, but it does represent a correct implementation of that algorithm as we want to put it into Verilog. So, even though the number is very far off, this does constitute a correct implementation, not a verification problem. So our quantized model, so the overall quantized model needs to be validated. And this is not just verified, this is validated. I meant to bold that validated because it's not verified. So remember that validated is, did we implement the right thing? So as we quantize this, as we take the number of bits that we're using to represent our features or our weights, we need to figure out, are we still getting a correct inference from our neural network? And in order to answer that question, you need to run a large number of inferences. And the predictions will be different from the Python or from the C++ algorithmic model. And we need to determine if the CNN accuracy is acceptable. And we're going to modify the networks, the layers, the channels as needed. And we're going to repeat that. And this is an iterative process where we're going to be searching for an optimal combination of bit representation, networks, layers, and channels. So one day, machine learning frameworks are going to support quantized numbers. We're actually starting to see this. So there's packages like QKeras, Lark, and Hawk are examples of extensions to some of the standard machine learning frameworks that support quantized numbers. Now, the thing is that your abstract model, this C model that we're creating, or the Python model, has to exactly match the Verilog that we're going to be implementing. Because if the abstract model does not perform the same bit transitions that the Verilog implements, you're wasting your time verifying that model. Now, if we look at these extensions, people are saying, yeah, you can use them to prove the correctness of your algorithm as it's going to be implemented in hardware. But if you're not using the same rounding type, if you're not using the same saturation, all of the details of those operations need to be the same between the abstract model and the Verilog, or ultimately your target hardware. So these environments work for a specific TPU, right? They do, in fact, fully match how that TPU is operating. But these environments, QCaris and so forth, are not sufficiently expressive enough for a completely bespoke accelerator, right? Getting those to, you could modify your Verilog to exactly match what the Python's doing, but that's actually not the point. You want your model to correctly implement what ultimately you're going to put in hardware, not the other way around. So for now, we need to do this arithmetic and this verification at the C++ level. Like I said, one day this will be moved up to, this will be moved into the machine learning frameworks, but we're not quite there yet. So C++ to quantized architecture consistent. So once we've proved that the quantized C++ is working, we now need to match it up with the C++ architecture. So we're going to run a quantized node with that architected node. And so we've got our quantized CNN, our architected CNN. Again, the architected CNN, we're bringing in parallelism, we're unrolling loops, we're introducing pipelines, we're introducing data paths. And as we do that, we get the potential for coding errors, but we're also going to get order of operation differences. So here, both of these are going to be running with the AC data types. They're going to run with the fixed point, with the reduced precision, and they should give you just the order of operation rounding errors. And so this becomes an easier step than the last one, but not an unimportant one. Now, the verification before we go to high-level synthesis, we've got a number of static design checks that could be done. And these are going to check for both correctness of the code, as well as looking for programming constructs which would give the synthesis problems and so forth. And also at this level, we want to look at the stimulus that we've given this architected CNN, and we want to make sure that we've got complete coverage of it, statement, branch, and expression. We can look at cover groups, cover points, bins, and crosses as well. So we want to fully take advantage of the fact that we've got this abstract model. It's going to run much, much faster than our RTL, and we want to make sure that that's been fully validated before we go through high-level synthesis and down into RTL. Now, when we do go down into RTL, we're going to use this architected CNN as our implementation, as our oracle, as our expected results against the RTL itself. And we do have formal methods built into the high-level synthesis tool that will do verification between the input C++ and the resulting RTL. Now, where formal techniques have not proved the equivalence, we need to do dynamic simulation. And this is where we're going to bring in UVM. Our predictor will be this architected CNN, and we will then look at RTL coverage, where we've excluded whatever was covered by formal, and then prove that we've got complete coverage throughout that RTL. Now, you're also going to need to worry about debugging when things go wrong. And what I have found is that as we look at two different models, they're different representation of the same CNN, and we expect the data to flow through it and get the same prediction out of both, taking into account the differences that we're trying to analyze and verify that we've done correctly. And one of the things that we've done is logged all the intermediate values either into memory or a log file. So the outputs from every single layer get stored somewhere unique, and they are kept from the start of the inference to the end of the inference. The next thing is we want to have scripts that will compare all of the intermediate values through all levels of the network. And what this lets us do is automatically identify our first point of divergence between the two models. So if we get to the end and we see that we've got a completely different prediction, what we want to know is what node did something wrong. And you do that by looking at all the intermediate values, going to the first point of divergence, and then you can then go in and try to figure out exactly why that divergence occurred. Intermediate values from the Python can be recorded, so all of the different machine learning frameworks in some form or fashion have the ability to log the intermediate values of each layer. And so we can store those out of Python and compare those with the C implementation or even with the RTL implementation. Usually you're not comparing Python to RTL. Usually it's Python to C++, C++ to other C++, and then C++ to Verilog. But keeping those in, keeping all the intermediate layers and having an automated comparison, which can point you right to the first point of divergence, is really going to save you a lot of time. So you want to plumb that in as early as you can. So our HVL, our high-level verification UVM flow, is taking this Verilog, using our architected C++ as our predictor, and then using the far more traditional UVM test bench. So now I'm going to take a few minutes to take this theoretical talk that I've done so far and tie it into something very concrete. We're going to be talking about verifying a wake word inferencing algorithm using the techniques that I've just described, including high-level synthesis and the verification techniques that I've talked about. So the wake word algorithm, of course, we're all familiar with this. Hey, Google, Alexa, and so forth. This is an algorithm that just sits and listens to the ambient noise and listens for a particular phrase that gets it kicked off. This is something that runs continuously, even when the system's not doing anything, and so it does need to be efficient. And especially when it's battery powered, you're going to need to make sure that this thing is using as little power as possible. We trained it with the TensorFlow speech commands data set, which is available at this website. What we did was selected utterances from 0 to 9, much like the MNIST digit recognition. So our inferencing is giving us a prediction on 10 different operations. Did somebody utter a 0, a 1, a 2, a 3, all the way up to 9? The base algorithm came from InterSpeech in 2015, and this is a conference that talks about audio processing in a variety of contexts. So this was convolutional neural networks for small footprint keyword spotting. So we started with a very efficient algorithm in the first place, and then tried to optimize it as much as we possibly could. So the wake word algorithm itself is going to process 1-second samples of audio data in the form of pulse code modulation data. So we've got 16,000 16-bit integral values that are going to be coming in per second. The algorithm is going to be run every 50 milliseconds. So fundamentally, we're going to be adding 320 new samples and dropping 320 samples off the other end of our rolling window of audio data. So our processing needs to complete in 50 milliseconds. The audio is pre-processed using a function called a Mel frequency substrum coefficient function, or MFCC. That generates a spectrogram. The spectrogram is then used as a feature map for our inference or convolutional neural network. So this is kind of a diagram of what we were talking about. So we've got our wake word, a microphone that pulls in data that gets quantized into 16-bit values. So we get a big long vector of 16-bit integers that gets passed through an MFCC, which generates a spectral array. That's going to be a floating point set of floating point numbers that's 101 by 20 by 32-bit floating point values. This is our feature map. This is kind of a heat map of it that we then pass into our neural network. So the Mel frequency substrum coefficient, this is an audio representation that's commonly used for feature extraction in neural networks. So the Mel scale is sensitive in the same way that the human ear, so it picks out a set of frequencies that humans have a really good ability to distinguish. And so this is why the frequency scale is used for features. And to obtain the coefficients, essentially what we're going to do is frame a set of windows. We're going to convert that audio data into the frequency domain, and we're going to calculate the amount of energy per frequency and per time unit across that incoming sample. And then we're going to run it through a Mel-spaced filter bank and then generate our coefficients using a discrete cosine transform. Then it gets passed into our neural network. So we've got our 101 by 20 words, which is our feature map, into our 2D convolution. This has a 20 by 7 convolution kernel for 186 channels. We then pass it into a dense layer, a second dense layer. So this is 17670 by 128. Another dense layer, a final dense layer with ReLU, and then into softmax. And so our heaviest weight load is in this first dense layer, and then our highest computational load is in the initial convolution. If we look at a profile of the wake word algorithm, we're going to find that the heavy lifting is done in the MFCC calculation, calculating the power, the energy that's in each frequency and in each time slice of that audio cycle. And then we've got roughly equal computations between our dense layers and our 2D convolution layers within our inference. So these three values are heavy lifting. They're the things we're going to move into bespoke accelerators. The overall computational load, MFCC, is 54% of the load, the 2D convolution about 20%, and the dense about 20%. Combined, this makes up about 96% of the total computation time if we were to run it in software on a RISC-V processor. The profile for the MFCC, we're going to see that 96% of that is in calculating the energy in the waveforms at different points and different frequencies. So this is the thing we want to move into an accelerator. So again, our Python to C++ consistency, we're doing this both for the audio pre-processing as well as each of the neural network layers. So we created the C++ node, the comparator, ran each of the C++ nodes in parallel with its corresponding Python nodes. Now we needed to run 80 audio samples to get full coverage across the C++. So this represented 10 different utterances with 8 different CNN variations. And the runtime here was 230 seconds, or about just under 4 minutes. The differences were found only in the bottom 4 bits of the mantissa of the floating point numbers that we were comparing. This is consistent with differences in order of operation errors that we might see as we changed the order of operations in a set of floating point operations. We used the C types to be able to link in the C++ functional library. The next thing that we're going to do is to quantize the algorithm. So we've got the algorithm as C++. Now what we want to do is reduce the numeric representation to be able to create a smaller, more efficient, both pre-processing block and inferencing block. So we performed a sweep for all of the fixed point values for both the inference and the power spectrum to determine our quantized accuracy. So the power spectrum, it needed an actual 8-bit floating point representation. We could not get that to work with a fixed point. It needed the dynamic range that you get with a floating point number, but it didn't need a 32-bit floating point or 64-bit floating point. We could actually go with an 8-bit floating point. And there was a very large constant array that needs to be applied to this. And so being able to shrink that from 32 bits down to 8 bits was a very significant reduction in the memory requirements for this function. The inference, we needed 16 bits for the convolution layers and 13 bits for the dense layer. We decided to go with 16-bit fixed point. Now, the architecture of the CNN was already very highly optimized. That 186 was right at the point where it started to break in terms of accuracy. So in this particular case, we didn't do any further architecture changes to the CNN. We're just quantizing down to the smallest implementation that we could get for the accelerators. So for the convolution, this is what our accuracy curve looked like as we went from 32 bits down to 2. We can see that right at 16 bits, it started to degrade in terms of accuracy. If we looked at the bit width versus accuracy on the dense layer, we can see that it stayed at a very nice 90%. It actually went up just a little bit as we got to 13, and then it falls off a cliff. Now, as we looked at the bit width, and this was a fixed point bit width for our power spectrum function in the audio pre-processing, what we find is that even as we went to 32-bit fixed point, we had a big drop in accuracy, right? The accuracy should be up at 90%. It was down below 80% and just fell off as we reduced the number. Interesting that it didn't continue that curve, but it bumped along. But nevertheless, all of the accuracy was completely unacceptable. As we went to floating point numbers, and again, we're building our own hardware, we can create any size operators we want. The floating point went down to 8 before falling off just a little bit and then falling off a cliff. And so doing the C++ to quantized model consistency, again, we needed the 80 samples. So it's 10 different utterances times the different CNN configuration. Here, the runtime was about half an hour. And this was the concurrency, looking at concurrency between the C++ quantized model, or the floating point model, and the quantized model. So we measured branch and line coverage and achieved 100%. Now the differences here were large, but they were within expectations. Comparing the assigned floating point representation to the quantized representation, the plus or minus values was 0.00024, and except for where we hit saturation. Where we hit saturation, it was dramatically higher. Remember that we had so our fixed point numbers in our convolution and dense layers, in the inferencing layers, here we had 1 over 2 to the 8th. So this difference is within expectations, and we were able to, it basically went value by value as it popped out and did the comparison and made sure that we weren't losing accuracy in an inappropriate way. But this stage right here, proving the correctness between the floating point and the quantized version, is probably the most challenging verification step that there is. So the next thing we would want to do is create the architected version of the accelerators. Remember, architected, we're going to bring in data movement, we're going to bring in buffering, we're going to unroll loops and introduce pipelining and things like that. And so when the data is accessed multiple times, what we want to do is, wherever possible, copy it into local memories or buffers. And the target is to reduce the amount of memory traffic, and reduce the overall data movement, because data movement consumes energy and takes time. Both of those are things that we want to avoid. And so what we can do is introduce line buffers and frame buffers to hold portions of the data being worked on, where new data can be shifted in as old data is no longer needed. So our first area where we want to look at this is convolution layer number 1. So we've got a filter, convolution filter, which is 20 words by 7 words. And what we're going to do is overlay this on the spectral array. We're not going to let it hang off the edges, so it's only where it properly fits. And we're going to slide it along this spectral array, multiply all of the 20 by 7, the 140 values in the filter by 140 values in the underlying spectral array. And that's going to give us a result value. Now that one result value gets moved on to the next stage. It doesn't get reused. Each filter is going to be reused as it shifts across. So we're going to use each value in the filter is going to get, so each filter is reused 95 times, and then the filter's discarded and we can go get the next one. So essentially, each value in the spectral array is referenced just over 1,300 times each. And the size of the spectral array is 2,020 words. So it's small enough to create a memory. Remember, it's 16 bits. So this is just going to be a little under 4K of memory that we need, 4K bytes of memory that we would need to store this spectral array. Each filter is referenced 95 times, but each filter data element is referenced 7 times that. That's the total size of the filter is 140 words. The output lines are calculated from a single filter. So we're going to read the filter in, we're going to store those 140 words, we're going to use them 95 times, and then discard them. And so so the total amount of memory that we need to have is memory, a 4K memory for our spectral array, and then 140 words worth of registers is what we use to hold the filters. And then we perform all the multiplication and drop it out there. So the fastest architecture that you could create would be 140 multipliers. And those filters, were held in registers, a portion of the spectral image in registers with the remainder in line buffers. And then we could just shift it around and do the multiplication. What we ended up doing was a bit more efficient. So we just used 20 multipliers. So we're doing a single column at a time. It would take 7 clocks to get a single output value. Due to the high level of data reuse, if the data is held locally, this function is compute bound. We're not bound by how quickly we can read the data in or shovel the data out. Now this is in contrast to our dense layer. So in our dense layer, the first one, we've got 17,670 values coming in a vector, and we're going to multiply it against 128 vectors of the same size. So this first data value that comes in is going to get multiplied by the first value of each one of these 128, and then we will have computed, as we do this multiplication, we'll create a partial sum. We're going to multiply the second by the second, and then add that to this value. So if we look at the architecture that we want here, elements from the convolution are referenced 128 times. Each weight element is referenced just once, and the output is just 128 words. So what we want to do is have this result vector, this 128 word, as registers within the accelerator to hold the partial sums. We want to store this vector in a memory and be able to stream it out. And then we want to read in the first value of these 128 vectors, read all those in at once, multiply it by these, store the result there. We then want to read the second value of all of these vectors, multiply it against the second vector here, and add those partial sums to these registers. So we can have one memory here. We need to read in 128 values from memory and update these 128 values. And that gives us both our parallelism and our efficient memory value. So this layer is, this dense layer is completely limited by how fast we can pull those weights in. So we're going to read the features and store those locally, and then the weights are going to impact how quickly we can perform that operation. Now the weights need to be packed in memory in the correct order so that we can get 4 of those values. Remember, they're 16 bits, we've got a 64-bit bus. We're going to read 4 of those values in from memory. So we want to read the first 4 values, then the next 4 values, then the next 4 values, and then we want to go into the second index in these vectors. And so by rejiggering exactly how those are laid out in memory, we can stream this entire vector in and maximize our use of the bus and minimize the time we spend. But ultimately, this is also about balancing our communication and computations. So the computations in this case are limited by the arrival of data. And so here, we don't want any more multipliers than the number of filter elements that we can bring in on each clock cycle. So in this case, it's 4. So we've got our streaming input. We're going to put these in a small cache memory, and then we're going to feed it into our multiply accumulate, and that's going to go into our output bank where they're going to be stored against the partial sums, and then we're going to write those partial sums out. So what we're going to see is lots of operations on this reading, and we don't want any more than 4 multiply accumulate units because we can't get enough data in to keep any more multipliers fully utilized. So again, here our C++ quantized to our architecture consistency, running these two in parallel. We ran the same 80 test cases. Runtime here was 1.2 hours, and we fully covered, we did full coverage against both the architectural and the quantized models. The differences were limited to plus or minus 3 LSBs on the inference and plus or minus 1 LSB on the power spectrum. And so we got very good correspondence between the two different models. And our C to RTL comparison, we're using our architected C++. So again, that's this CNN that we've proved matches our quantized version. And we're going to use that as our predictor. And then we've got our Verilog. Again, we still may see a couple of least significant bits flip because we do have order of operations difference between the C++ and the Verilog, but we should be able to do this comparison just masking off the low bit or 2. And so here we can have our predictor running against the implementation in Verilog. And so here we get our, the core algorithms were verified through formal, but there was lots of surrounding logic, which wasn't. So here, we didn't need all 80 test cases in order to get, because our softmax function, which is where we had a fan out through those 10 different utterances, that is remaining in software. So in order to fully verify the RTL, we only needed 8 of the test cases. The architected C++ was used as our predictor. The simulation covered the CNN architecture, all the different variations. And this was 34.4 hours of simulation to be able to do this. So if we needed to do our 80 test cases at this level, you can see that it would be up around 300 hours, 350 hours of simulation. And then if we needed to do multiple runs for it, as we were honing in on exactly what quantization we needed, you can see that that would quickly get prohibitive. So in conclusion, moving from Python to RTL in a single step is going to introduce a lot of verification problems. The inferencing algorithms between Python and Verilog are not going to produce bit-level equivalency if we're doing the proper optimizations to the Verilog implementation, which makes sense. And we're going to have to do a lot of verification because we need to run a statistically significant number of inferences against that Verilog implementation, and the simulation performance is just too slow to support it. High-level synthesis introduces intermediate C++ models where we can prove equivalency through each stage of the development cycle and finally against the resulting RTL. This means we've got faster verification and we spend less time in verification with fewer verification cycles. I'd like to thank you for your time today in listening to our talk. If there are any questions or comments, as I mentioned, Petri Salanti was involved in the creation of a lot of this content. You can reach him at petri.salanti@siemens.com or myself, russell.klein@siemens.com. Again, thank you for your attention and enjoy the rest of the show.